So my name is Dave Zacks. I'm a distinguished engineer with Cisco. I'm based out of Canada, based out of Vancouver, actually. And what I'm going to talk to you about today is ASICs, silicon, how Cisco designs it, how we build it, why we build it the way we do, and the functionality it provides. So I think ASICs are pretty exciting. I've jammed a lot of material into the next 30 minutes, so it's going to be kind of a fire hose. That's why I kind of put a picture of a rocket on here. Anybody know what kind of rocket this is? So I'm into rockets and high-performance aircraft, all that kind of stuff. Anybody know what kind of rocket that is? Bonus points if you know.
None from the ESA, so I am out.
No, that's an ESA rocket. That's Ariane 5.
Ariana?
That's Ariane 5. That's an ESA rocket. That's actually the one that put up the first satellite for Kazakhstan about a year ago. So the other tag we put on here is high bit rate because I'm going to go through things rapidly. And if I'm going through things too rapidly, just stop me and let me know. Okay? So a little bit more about myself. You can read all about that. Basically, what I will say about being a DSE for Cisco, that might not be a position you're familiar with. What I do is I work on next generation products and solutions for Cisco. So most of the stuff I work on in conjunction with folks like Peter is stuff that's kind of anywhere from 12 to 36 months out in the pipeline, stuff that we're going to have to sell you and have on the truck to sell you a year to 3 years from now is most of the stuff that I work on. So I've been with Cisco about 16 years. Inside Cisco, we say that we live in dog years. So if you're a little dog, that's 5 years per year. If you're a big dog, that's 7 years per year. So on that basis, I've been with Cisco anywhere from 80 to over 100 years so far. And I'm starting to get the gray hair to actually prove that. So what is an ASIC? This is a Wikipedia definition of what an ASIC is. I define Wikipedia as a source of partial truth, right? So basically what Wikipedia says is it's an ASIC is a circuit that's designed for a specific use. In other words, it's different than a general purpose CPU. So like an Intel CPU would be built to be a general purpose device to be used for many things. ASICs are typically built for one particular purpose, and that's what we're going to talk about here. So why do we want to talk about ASICs in the first place? I mean, they're hardware, silicon. Why do we want to talk about them and know more about them? Well, one of the things that we've seen is that our executives, folks like Rob Soderberry, who actually runs all of enterprise networking for Cisco, he's got about a $20 billion business under him. We constantly see our executives standing up on stage, holding up a piece of silicon and saying, this is an excellent example of Cisco innovation, but there's no real drill down below that, right? So if you want to know why that's an interesting example of Cisco innovation or what we're doing in there that's innovative, there really wasn't any material out there that would tell you why that's innovative or what was interesting about it. So for example, the chip that Rob's holding up there is a chip that we're going to talk about in extensive detail called Unified Access Data Plane, or UADP. Anybody aware of the Catalyst 3850 switch? You know the Catalyst 3850? Okay, this is the heart of the 3850. So that particular chip we're going to talk about in detail as we go into this presentation. You'll see why that's so innovative. But before we start talking about ASICs, we really have to have a common language that we can speak around ASIC. So I'm actually going to talk a little bit generically about how we, Cisco, the industry, designs and builds silicon. How do we do that? So when it first starts out, we think about marketing, defining all sorts of requirements for a chip. So they would go out and say, we've got industry sources, we've got research and development, we've got the state of the art of what's possible, we've got customer requirements, we've got all those things we have to bring together and synthesize and then say, this is what ideally we'd like this chip to be able to do. Now, marketing always asks for more than engineering can deliver. That's normal. So marketing will have a set of asks, they'll go to engineering will sanity check it, they'll come back to marketing and say, here's what we can actually accomplish. So we've shown this as a one-way arrow here, but in reality there's a give and take, okay? And at the end of the day, we're going to come up with a specification for what we need to do in that chip. That specification is called the microarchitecture document. So this particular chip, that's the heart of the 3850, one of the things I did when I started digging into that chip is I went to one of the engineers responsible for it and asked for the microarchitecture document. Can you please give me this that I can read? Now, he sent it to, as most of these guys will do, people that work on ASICs at that level aren't normal humans, okay? These are the kind of guys that you want to basically lock in a room somewhere, slide pizza under the door once in a while, and then eventually they produce an ASIC out the other side, right? They're not normal people. So I asked for this, and instead of sending me a nice email and a reply, as they often do, he just sent me a PDF. Boom, here's PDF, go read it. So I pull up the PDF. How many pages do you think it was? The microarchitecture document, for that particular chip in the 3850.
700.
How many?
700.
700 pages? No, keep going. More.
No way.
More.
Oh.
How much more?
10,000.
10,000, exactly. You must have read it. The actual current version of it is about 12,000 pages. The executive summary alone was over 100 pages long. I don't know what kind of executive reads a 100-page summary on a chip, but it was extensive, right? There's a huge amount of detail in there. Now, how many people knew that when we actually designed silicon, if we take a chip, like this chip right here, okay, this is a UADP chip, UADP ASIC, we have right here. This has 1.3 billion transistors on it. How do you think we designed something like that? Do you think that there's a team of humans that lays out the position of 1.3 billion transistors on a chip? It's not possible. It's beyond human ability to do that. So the way that chips are actually designed is, this is hardware, but it starts out as software. There's two different coding languages that are in common use within the industry. These are what are called hardware description languages. And the difference between this and a typical language like maybe C or C# or C++ would be that in a hardware description language, you have the concept of timing associated with the chip. So these two common languages are Verilog and VHDL. Cisco actually uses Verilog. So we would actually code everything that that chip's supposed to do in software. Now that software can actually be run on a simulator. So before we actually have so remember at that point, we don't have the hardware. We're writing the chip as software. We actually write the software, run it on a simulator. That simulates the chip at maybe 1/10,000th of the performance of the actual hardware, but that's how we initially design it and debug it. Now, once we've actually got the software kind of down pat for the chip, and we think we've got the design that implements everything that marketing has asked for, we then run it through a process called synthesis. How many people are familiar with compiling code? You take code and you compile it. This essentially compiles it, but what it compiles to isn't like a piece of software that would run on your smartphone or your laptop. It compiles to a hardware design. It compiles to a circuit diagram. That's called the synthesis process, and the output of this is what's called a net list. So the net list is like the object code. That is the hardware description. And we would literally take the net list and send it off to a company that will actually turn that into a piece of silicon for us. Right? So we said there's multiple companies in the industry that do it. Some of the ones out there that you would know, Intel obviously would do this. There'd be anybody heard of TSMC, Taiwan Semiconductor Manufacturing Corporation, company like that, maybe Global Foundries, for example, which used to be IBM and recently got sold. They would turn that into a physical piece of silicon for us from the net list. Now, one of the things that has to happen is the chip gets designed in blocks. So there's various different blocks of silicon that are made and designed to work together. This is a process that humans actually do, called floor planning and placement. So you basically have all these different functional blocks on a chip, maybe a piece that's designed to talk to memory, or a piece designed to do a certain level of processing on a chip. A human will lay those out, interconnect them, reduce crosstalk between the different areas in the chip, and basically build out the floor plan of the chip, if you will. Then we actually see a process that you may be familiar with, where we actually shine a light source through a photo mask to etch that chip onto the silicon wafer. Okay? That's the thing that you often see when chips are being designed. Now, this isn't done with light anymore. The type of chips that we're designing now and building now in the industry, we, Cisco, and the rest of the industry, this is actually done with ultraviolet radiation, which is a shorter wavelength than visible light, and they're actually moving towards doing this with what they call X-ray lithography, where we get to smaller and smaller sizes, you have to use smaller and smaller wavelengths. But ultimately, you can think of it as like shining a light to etch that particular pattern onto the chip. Now, once we have that particular piece of silicon here, you can see that this one here has multiple different chips that are built out on it. That's very, very typical. This is actually a small wafer compared to what's being done now. Most wafers now are like a 12 or 14-inch wafer, so this is a little bit older picture. Wafer's a little bit smaller. But then there will be a machine that comes over all the chips that are etched onto that wafer and effectively boots up each chip. And it runs like a power-on self-test like you would do with your PC. So it goes onto a chip, boots it up, sees if the chip is actually operating properly. Was it designed and manufactured properly, at least to a certain level of operation? If the chip is functional, it'll be accepted. If the chip is non-functional, and we'll talk about why some of them will be non-functional in a bit, we'll actually drop a blob of red paint on the top, and that says that chip is bad, right? So as we go through here, some of these chips are going to work and some aren't. Now we think about some manufacturing considerations here. Sometimes in life we question if size matters, and it does in silicon, okay? So in the ASIC world, the smaller it is, the better it is. So we're really talking about transistors and how many transistors we could put onto a silicon die, right? Now everybody's familiar with Gordon Moore, founder of Intel. Moore's law says that the power of computing will double at the same price point every 18 to 24 months. This is a law, quote unquote, that he came out with 40 years ago. This has driven the entire technology industry for the last 40 years, Moore's law, right? And what's fundamentally driven it is our ability to keep doubling and doubling and doubling and doubling the density that we produce on silicon. So when you take a look at this, the actual silicon widths here are measured in nanometers. So a nanometer is a billionth of a meter. Now to put that in something that's more human understandable, the width of a human hair is about 80,000 nanometers. So we're designing circuits here that are 65 nanometer, 45 nanometer, 32 nanometer, 22 nanometer, or even less. How many people have an iPhone 6? Got an iPhone 6 or 6 Plus? Most people have that these days. Okay, the actual chip, the processing chip that's inside your iPhone 6 Plus is built with a 14 nanometer process, which is close to being state of the art. The place where we'll go from here will be from 14 nanometer to 10 nanometer, 7 nanometer, 4 nanometer, 3 nanometer, 2 nanometer, and ultimately at that point you're down to atomic sizes. We'll probably be there by about 2020 to 2022. Even to build a 10 nanometer chip, you have to shock isolate the building, because even trucks driving by on the road outside can vibrate the building enough that it messes up the manufacturing process. So we're getting to some very, very high densities here. Now, why do we care about that? Why do we care about driving to higher and higher densities? I put it up to three things. First one is we get higher performance because we're actually reducing the amount of silicon and the distance between the transistors on a chip. We're going to lower power because the circuit diagram, there's actual circuit elements are smaller and smaller. It takes less and less power to run them. There is a corollary to that we get more increased leakage between elements. Anybody familiar with quantum physics? I love quantum physics, right? Okay, if you're familiar with quantum physics, you might be familiar with a effect called quantum tunneling. When you get these very, very small circuit sizes, quantum tunneling effects actually start to become significant and potentially even dominate at these very small circuit sizes. But the most important thing from a typical human point of view is we get to lower price. And that seems kind of ironic because I'm going to a higher and higher tech process. Shouldn't it cost more money to manufacture a higher density chip than a lower density chip? The actual answer is no. We get to a lower price because it's all about this question of yield on the chip. So when we take a look at that particular silicon wafer, let's zoom in on that a little bit more. That silicon wafer that we're manufacturing on is an ultra pure silicon wafer, but it can never be 100% pure. There's always potential impurities that exist on the chip. So these impurities are scattered at random over the chip, and we're going to photomask chips on top of that. So some of the chips that we're going to photomask on top of that silicon wafer are going to miss the impurities, and some of the chips are going to hit the impurities. And we don't know in advance where those impurities are in the wafer. So some of the chips that we manufacture are going to be good, like this chip, and some of them are going to be bad when we test them, like the chip next to it. Make sense? Okay? So when you think about that and you extend your thinking a little bit, you can say, well, if I can actually shrink the size of the chip, manufacture that same functional chip in, let's say, 1/4 of the space, by chance of getting, here I would have had a chip that was bad because it hit 2 impurities, but over here, in that same space, I might actually get 2 functional chips and 2 bad chips, or maybe 3 functional chips and 1 bad chip. So my yield goes up. It costs me the same amount to manufacture a silicon wafer with a larger size or a smaller size. So if I can shrink the size of the chip, my yield goes up, my costs go down. Make sense? It's all about getting to higher yield. Now there's a give and take there. Because, for example, if I manufacture something at a higher yield, I'm typically taking a higher risk to be on a leading edge silicon process. So for example, if you go to a company like TSMC and say, I want to build my chip on a 14 nanometer process, and you're the first kid on the block that's manufactured a 14 nanometer chip with them, you're taking a risk because their process is also new. So a lot of times when we introduce a chip like this, for example, when we built the U80P ASIC, the first version of this we built was on a 65 nanometer process. And then we got the chip right. We got the chip functional. Then we went back and did a respin on it, dropped it to 45 nanometer, Then we do the latest respin on it, which is dropped it to 32 nanometer, and actually put 2 chips on 1 die, what we call 2 in a box. So we actually put 2 functional chips on 1 die. And after that, we will continue to chase that down to higher and higher densities, lowers our manufacturing costs, increases our yield, better for everybody. Okay? So think about what we just went through. We talked about how we do ASIC coding, synthesis, floor planning, packaging, system testing. At the end of it, how long do you think that process takes? From the time that somebody says, I'd like to have a chip that does X, I'm dreaming of a chip that might be able to do X, how long do you think it takes from that initial thought process to the time you have a piece of silicon in your hand?
5 years?
Depends on the chip. This chip took about 5 years, but that's an unusually long time because I'll show you this is a very, very capable and complex chip, the UADP chip in the 3850. The average time to build a piece of silicon is usually about 18 to 24 months for a typical chip. That's still a long time. Now imagine what happens with a typical chip when you go through this whole design process, you test it. Well, think about, remember I said the chip starts off as software? What if you have a bug in your software? And after 18 to 24 months, you get the chip back and it's got a bug. What then? What do you think happens then? Because remember, this chip isn't designed just to be a chip. This chip is part of a whole system. You've got a whole switch being built around that. You've got people designing power supplies and enclosures and thermals and writing software and all this stuff. And then you get the chip back and it's got a bug.
You cannot do much about it, yeah? It's inside, you cannot change it. Will be rolled out with a bug.
It might be rolled out with a bug, or depending on the nature of what the bug is, we might have to go back for a respin. So if the bug affects something really, really critical and fundamental in the chip, we'll have to go back to a respin. Otherwise, what we might do is just turn off that particular function in the chip, not claim support for it in this version, so basically just functionally turn it off, and then in the next spin of the chip, we'll fix a bug and then claim support for it.
So it can be.
So it depends.
It can be that a whole production line has to be rolled back. Yeah.
That's the worst case. The worst case scenario here, when we say ASIC engineer's worst nightmare, is that you've got a whole project rolling. You have dozens or hundreds of people working on a product, and you get the chip back, and it's got some fundamental flaw. And that has happened from time to time, and it can cause the whole project to slip, which is very expensive, right? So we put a lot of effort into testing and simulating the chips up front, so that we don't have that happen, but it can happen. Now,
are respins not? I had the impression that they're quite a common thing to happen.
ASIC respins?
ASIC respins.
Depends.
We
try not to make
respins after an ASIC launch or after.
People will mean different things by respins. So, for example, I mentioned the first version S came out on 65 nanometer, and it was totally functional, right? We had a good chip, good design. But then we want to do a cost reduction on the chip. So we will go back and respin this from 65 nanometer to 45 nanometer. That would also be called a respin, but it's not a respin because of a bug. We basically just want to reduce the size so we can increase the yield and drop the cost. Right? So people will mean different things. Sometimes a respin does indicate a functional failure of the chip design, and you have to go back and change it. Right? We try not to do that. It's very expensive, and it also is not good for customers. Right? You're expecting a product at a particular point in time, and you might not get it because we had to go back and do a respin. We try to avoid that. Now, one of the things we see about ASICs is that traditionally, the processing pipeline in ASICs is fixed. So what do I mean by that? When we design a typical piece of silicon, not this one, but a typical piece of silicon we would define, it is built to do a particular thing. So for example, it has a parser block here on the front on a typical ASIC. And that parser block might understand what IPv4 is, or IPv6 is, or MPLS is, but it would be hard-coded to understand those things. So the chip can do that, but if it's not hard-coded to do that, things can't support it. How many people are familiar with the 3750 switch? Okay, the precursor to 3850. Okay, 3750 switch does not handle MPLS. The chip that we build that on, which is called Strider 88, is not built to handle MPLS. So you might wish as much as you want that a 3750 could route MPLS packets, but it can't because we didn't hard code it. We didn't software code it to do that. Now, one of the things that we're doing as we go forward in the industry is moving beyond this traditional fixed processing pipeline into more flexibility. So when you think about what's the most flexible piece of silicon out there today, what's the most flexible piece of silicon that exists in the industry today? Do you think? x86 CPU, absolutely right. If we take a look like something like an x86 CPU, you could, with the appropriate software, you can pretty much make that chip do anything. But I say that it's very flexible, but it's slow. And you might think about that and go, no. I've got like a 3.2 gigahertz processor. It's fast. Actually, it's not, right? When we think about the kinds of things that we do in networking, as opposed to the kinds of things you do in a desktop computer, in networking, I'm constantly doing things like table lookups. I have a big MAC address table, or a big IP route table, and I need to do lookups against that. When I'm doing that with a general purpose CPU, it is in no way optimized for that. Right? General purpose CPU, all the memories are off chip, so every time I have to look something up in the table, I have to go off chip, off chip, off chip. It's very slow to do it, but it is very flexible. So typically on a lower end platform, I've got something like maybe an ISR. An ISR platform would leverage a general purpose CPU because it's well matched for the performance that that box needs. Now we need to go up from there. We go to something called an FPGA, a field programmable gate array. This is kind of an intermediate step between hardware processing and software processing. FPGAs are nice, they're very functional, they're typically hard to program. They typically have different programming languages depending on who you get the FPGA from. Field programmable gate arrays are an interesting technology, but give us some flexibility, but they're also very costly in terms of bits per second moved. So typically where we use FPGAs in our products is typically as gap fillers, right? If I have an ASIC that does something, and then I need to handle a little bit more than what that ASIC does, and I need to handle it at hardware speeds, I have two choices. I could go design a new ASIC, which might take a year or two and cost X number of $1 million, or I can take just those particular functions, put them in an FPGA, and put the FPGA next to my existing ASIC, right? That could be a design choice that we make, right? But they're typically very costly. The next thing after that is the typical network ASIC, which is very fast, but fixed function, okay? So if you take a look at these and put them on a spider diagram, you can see that none of these things are really hit the sweet spot, right? And network ASICs hit a sweet spot around cost and performance, but they're not very flexible, right? FPGAs hit a sweet spot around performance and flexibility, but they're not very cost effective. General purpose CPUs give us great flexibility, give us okay cost, but they're not very good from a performance perspective. So what we're doing, and what we've done in this particular chip, the UADP chip that we've introduced, is really introduced a level of programmability that basically balances all three of these factors. Now, I mentioned that a lot of stuff I work on tends to be next generation leading edge stuff inside the company, right? And so I remember first seeing this particular chip a while before we shipped it inside the company. And when I understood what we built in this particular ASIC, as an engineer, my instinct was to stand up and applaud, because we had finally built something that balanced all three of these factors in a very elegant way. So what we've done is we've introduced this concept of flexible pipelines. So that pipeline in the chip that the packet moved through, the processing pipeline, instead of being fixed, is extremely programmable. So we've introduced programmability at all these different stages. Now I can modify the behavior of the chip without doing a respin. I can do a software download into a chip, get a whole new set of functionality at hardware speeds, but I don't have to go back and respin the chip. If you understand what a revolution that is in terms of ASICs, that's why when I saw this chip, I just went, wow, that's really exciting. We've really stolen a march on the industry. It's also why it took 5 years to build this chip. Peter was intimately involved with the development of this chip, right? Peter's been involved with it for longer than I have, and Peter's kind of my phone a friend in the session. So, for example, if there's more stuff that you want to know about UADP, and we will try and wrap up as quickly as we can, but if there's more stuff you want to know about this particular chip, if you can ask Peter any question about this chip that he can't answer, I will personally give you €2. It's an interesting one. How many people are familiar with the concept of recirculation in chips? Okay, basically what recirculation does, let's say, for example, everybody's familiar with tunneling, yeah? Geary tunnels, that kind of thing. Okay, you suck a packet into a chip and you decide that the output interface is a tunnel of whatever type. Let's say it's a Geary tunnel or whatever it is, right? So you're going to put another header on the front of the chip, but now you have to forward the packet to the tunnel destination, not to the original destination of the packet. Make sense? Okay, so we then need to recirculate the packet for a second pass through the chip. This chip was optimized for that because all the interesting stuff that's happening in the industry today, I know you guys deal a lot with data centers and overlays and stuff like that. They're all forms of tunneling in one form or another. We knew that when we built this chip. We optimized this chip to support tunneling with a high-performance recirculation path. The time it takes to get a packet out of the end of the pipeline and back into the front of the pipeline is less than a microsecond. It's about 500 nanoseconds to recirculate the packet back into the chip again. Extremely fast. How many people are familiar with the speed of light? Okay, light travels at 186,282 miles per second in a vacuum, or about 300,000 meters per second. Speed of light in silicon is about 0.7 C, about 70% the speed of light. So in a nanosecond, 1 nanosecond, light moves about 8 inches, or pardon me, electrons move about 8 inches in silicon. So we can recirculate a packet from the front end of the chip back into a chip in about 500 nanoseconds. It's amazing technology, right? Very, very fast. So UADP, 5 real key capabilities we've introduced here. Microcode programmable pipeline with a flexible parser. That's really key to what this chip delivers on. So that means that the actual pipeline in here is programmable through microcode. We can have people like Peter or other people that are maybe less articulate than Peter, the kind of people you want to slide pizza under the door through. Those people can go and recode microcode on this chip and make the chip give us a whole new set of functionality without doing an ASIC respin, using this concept we have called flexible parser. We also knew that one of the things we wanted to build in this chip was a high-performance stacking interface. Do you remember when we talked, Peter was giving his talk earlier, talking about 3850 and 480 gigabit stacking, all that kind of stuff? We built a 240 gigabit per second engineering number stacking interface directly into the ASIC so we could chain multiple of these together. We introduced on-chip micro engines. So one of the things that's very common if you're doing tunneling, if you're a network engineer and I say to you, tunnel, what's the next thing you have to think of? I say to you, tunnel, MTU. You think of MTU, maximum transmission unit, because I just stuck another header on the front of the packet, and now I might have, because if I exceed the MTU size of the output interface, I'm going to have to do what? Fragment. I'm going to have to fragment, and then I'm going to have to reassemble on the other side. Fragmentation is actually fairly light work. Reassembly is heavy work for the chip. We don't spend any of our cycles in the programmable pipeline handling fragmentation and reassembly. The frag and reassembly, we have a micro engine on the chip for that. We also have a built-in micro engine that handles encryption. So we do cipher block chaining with AES 128 built into the chip. High performance recirculation path, as I mentioned before, excellent for tunneling, and things like integrated on-chip NetFlow. One thing that people really value is visibility into what's happening in the network. So we introduce full flow NetFlow. This is no compromises NetFlow, 24,000 entries directly onto the chip itself. And all these functions and more, these are a whole bunch of other things that the chip can do. Some of these we've productized already. Some of these we know the hardware can do, but we may or may not have written the supporting software for it. We have tons of functionality in this chip that we haven't even unlocked yet. So end of day, what does this actually mean? It means that we've introduced an ASIC that gives us an unparalleled level of flexibility and investment protection, right? That's really key. This is so exciting. Like if you deal in the world of silicon, you typically don't get something that balances all these factors like that. So UADP, very, very exciting. One of the things we introduced with this, when we introduced the 3850, is the ability for this chip to handle both wired termination of traffic and wireless termination of traffic. So the ability for this chip to not only do things like NetFlow and advanced QoS, but gives us the scalability to do that for both wired and wireless traffic. So instead of taking my cap-wap tunnels all the way back to a central controller, I can actually terminate those cap-wap tunnels on the chip. Now inherently, this chip is so flexible, it doesn't even know what an IPv4 packet is. It knows what a V4 or a V6 or a cap-wap packet is because we microcode program it to know. And one of the first things we did in this chip was say, hey, wireless is becoming the common on-ramp into the enterprise network. I want to have this chip handle both wired and wireless traffic. In future, we could have it do a bunch of other things. So we could have this chip, now we're not supporting these functions yet, to be clear, but with this chip, I could easily have this chip handle things like Lisp or VXLAN or Trill or shortest path bridging. It's a very, very flexible piece of silicon that I could do all that with, just introduce a microcode update, what you would see as an iOS update, onto the platform, and suddenly the chip has a new set of capabilities. Very exciting. So we've already used this chip in a variety of products, 3850, 3650. If you're familiar with Catalyst 4500, if you're familiar with Supervisor 8E, that includes the UADP ASIC on a daughter card in the SUP 8E, as well as a 5760 WLAN controller. So we use it at a lot of different places in our product lineup. So I just sum up on this particular piece of silicon that we built that gives us great performance, great scalability, very appropriate for a place we intend it to be used at the entry point or the access layer of the network, and features and flexibility. So I'll end it there. If you want to know more, Peter and I are doing a session on Wednesday where we go through that. We spend about 90 minutes in the session and go through this chip and another very exciting chip we introduced on the routing side and talk more about it. And like I say, if you can ask this guy any question about the chip he doesn't know, €2. That's it. Thank you. Questions?
Yeah. Actually, I have a question on the NetFlow exporter from a chip design perspective. Yeah,
Yes.
I see a lot of, let's say, merchant silicon. They can only do sample rates. Yeah, you have clearly have the hardware ready to do the let's say full-blown flow with all the packets that crosses the ASIC. And the second
100%.
question would be, if you design a chip, you also had to make the decision, can I add between the header also, let's say, like an S-flow payload to that, what I would like to export? This is a decision that has to be made on the design phase, yeah? And afterwards you cannot change it.
Yeah, why don't you talk to that, Peter?
So what we're already shipping today, basically both Ingress and Egress, and remember we're an access layer switch, so I really want to do NetFlow on the downlinks.
Yeah.
So both Ingress and Egress, I'm doing 2 lookups per packet at line rate. I can sample them, I can do full flow. What I then do is basically the chip itself exports all its key data, exports via a DMA engine into DRAM. I'm then doing NetFlow export off all the stack members. So the chip itself exports into local DRAM, I then format that packet up. So we're not S-flow, right? S-flow is a much different thing.
Yeah.
So our goal is full NetFlow, 2 lookups per packet per direction.
Okay.
And what goes in the key is under software control. So for instance, when I'm doing wireless, I put in things like the .11 header. So I basically use a couple of TCAM lookups to decide what to put in the key. I can then put things like a microflow police room. That's all productized and shipping now.
And one additional question, this is kind of the same related. What about span ports and capabilities? How many ports can you do full span and?
Right.
So
Go ahead.
So the way the chip is structured, basically every packet that comes in goes through a classification. It's either coming in or out of a port. It gets assigned to any one of 8 span sessions, any combination, right? So one packet could be in 3 different span sessions. Every one of those sessions can then go to a set of ports. So the traditional output port will be a straight port, a normal span or an R span. Where we want to go is more than the R span type thing, because mostly I want to haul that stuff back somewhere else.
Right.
So I think we're going to end up with basically a flexible, a flow-based selection of what you need, and we'll send it somewhere else.
Right.
Yeah.
But to be clear, we don't have that productized yet. The chip could do it.
Give me a little time.
We just haven't written the software for it.
So only the software is the problem,
Yes.
as most times for you guys.
I'd say there's 2 problems. One is getting the software written. The other is figuring out whether or why we should write that, because there's always 1,000 things we could do. So it's a matter of working with product managers, right? People that Peter and I work with, to say, I've got customers X, Y, and Z that really want to use this feature. Here's the use cases for it. Here's the justification as to why we should go spend the man months or whatever it's going to take of our software engineers to write and code that feature into the chip.
And just to follow on, remember the discussion earlier? Hey, this thing you're interested in, give me details. If you think about what you want to use and tell us, that gives us context, right? Because we can't understand what every customer wants. And so you guys saying, hey, this is an interesting idea. If you did this, I could do this, this, and this.
Right.
That's really valuable information.
Absolutely.
So this conversation is not supposed to be one way.
Right. That's one of the reasons why we want to get our principal engineers like Peter out into the field. It's one of the reasons that, for example, in my time in Cisco, I spent 16 years as a field engineer inside the company, right? So I've worked with customers a lot over the years, and there's always a give and take there about, what do you need? How would you prioritize it? If I asked you to choose between A, B, C, or D, how would you prioritize those things for me? And you'll get different answers from a service provider customer, an enterprise customer, a commercial customer, a government customer. So they all have different care abouts. At the end of the day, we got to synthesize that and figure out with the amount of engineering resource we have, what are we going to design and build? At least with this chip, we've got something that's highly programmable. So once we make the decision we want to build it, we can probably make the chip do it, right? And that's unique. A lot of times before, when you came to us with those recommendations, we go, great, that's awesome. We have to go build a whole new chip for that.
I want to follow on. So one other thing to think about. So we introduced this family back in January of 13, right, in London. It was a very cool show. We haven't stopped, right? We keep building things. And so even though I might not be able to do something in this chip, if you tell me what you need, I can figure out what primitives to put in the next one.
Right.
So we are always building ahead.
Yes.
And so even if you come and say, look, this is really cool, I can't do that now, but that might influence the chip that comes out in 2 years and 3 years and 4 years.
Right.
So the feedback backwards and forwards of how you think the industry is going is valuable because we don't know everything.
And I will tell you that some of the smartest guys and girls that I've ever worked with in anywhere, in any company, are the people that work on our silicon teams. They're absolutely amazing, astounding people. When you take a look at the kind of stuff that they do and what they build into our silicon, how they design it, incredibly smart people. And they're a lot of fun to work with.
You always have to be before all the other guys, before the software teams even start. So
right.
always think ahead. Yeah.
Yes.
That's not true. If you do this really well, when we built this, we had the ASIC and the software team at the same time.
Okay.
So you want to actually have that combination, right? So if you just do the ASIC team too far ahead, then you get out of whack. You actually need to do it as a team.
And the other interesting thing I'll put forward there is that Peter is very modest. You can tell that he's got the modesty gene, kind of in overdose. But one of the things that Peter typically doesn't mention, and that I will, is that he performs a bridging role, especially in regards to this particular chip. Peter's a software-oriented engineer working on a hardware product. But this hardware product is so software programmable that Peter's role, in my opinion, is really key on this chip, and he's one of the key architects of the ASIC.
So we